today we're jumping into one of the biggest, most important transformations in the history of the Linux kernel. We're talking about the PREEMPT RT patch. This is the story of how a general-purpose operating system, the one that probably runs your phone or your servers, was completely re-engineered to hit the kind of ultra-precise timing needed for the world's most critical jobs.
So let's kick things off with a question. When you think about a high-performance computer, you probably think about one thing: speed. Raw, blistering speed, right? But is faster always better?
Well, think about it like this. A supercomputer is all about raw power. We're talking quadrillions of calculations a second. But a car's airbag system, that's about something totally different. It's all about predictability. It doesn't need to do a million things at once. It needs to do one single thing at the exact right moment, every single time. No excuses. And that, right there, is what this whole explainer is about. We're going to dig into what it takes for a system to be not just fast, but predictably fast. We're diving into the fascinating world of real-time computing. Okay, so first things first, let's get our definition straight. What do we actually mean when we throw around the term real-time? You know, the key thing to get here is time. In a real-time system, getting the right answer but getting it too late, well, that's the same as getting the wrong answer entirely. Think about a factory robot or a 5G network. For them, deadlines aren't just suggestions. They are absolute law.
And we are talking about an incredible level of precision. With the PREEMPT RT patch set, the Linux kernel can hit these deadlines with latencies under 20 microseconds. That's 20 millionths of a second. This isn't just about being fast. It's about having surgical timing.
So you might be wondering, if real-time is so important, why wasn't Linux just built that way from the get-go? Well, that gets us right to the heart of the problem, the standard kernel's latency issue. This quote from the kernel documentation, man, it just says it all, doesn't it? The standard Linux kernel is designed for things like fairness and overall throughput, not for perfect predictability. It basically assumes that small, random delays are okay. But in a real-time system, those delays are a total deal-breaker. So where is all this chaos coming from? Well, it turns out there are two main culprits lurking deep inside the kernel's architecture. You can think of them as our latency villains, and PREEMPT RT was designed to take them down. All right, meet our villains: spinning locks, or spin locks, and interrupt handlers. Now, in a normal kernel, these guys are essential cogs in the machine, but for real-time performance, they are absolute poison. First up, the spin lock. To protect shared data, it does two things that are just terrible for predictability. One, it disables preemption, which means the scheduler can't do its job. And two, it literally spins in a tight loop, burning CPU cycles, just asking, is it free yet? Is it free yet? Is it free yet? So if a super high priority task needs the CPU, too bad, it has to wait. And that creates a massive, totally unpredictable delay. And then we have villain number two, the interrupt handler. See, when a piece of hardware needs the CPU's attention, like, say, a packet arrives from the network, bam, it triggers an interrupt. The kernel immediately drops whatever it's doing, shuts down preemption, and runs the handler. It happens instantly, completely outside the scheduler's control, and it can shove aside even the most critical real-time task. Okay, so we've got these two major sources of total chaos in the kernel. How on earth do you tame that beast? Well, this is where the sheer genius of the PREEMPT RT patch comes into play. And this quote right here, it basically lays out the entire game plan. It's a brilliant two-pronged attack. PREEMPT RT goes right for the source of the problem by fundamentally changing how the kernel deals with both locks and interrupts. It really boils down to two core transformations that make this whole real-time Linux thing possible. Step one, swap out those spin locks for something much smarter. And step two, bring those wild interrupts under the control of the scheduler. So here's the first big move. PREEMPT RT replaces those wasteful spin locks with something called an RT mutex. Now, instead of spinning and burning CPU, a task that needs a lock just goes to sleep. This lets the scheduler run other, more important things, and it uses this really clever trick called priority inheritance. Basically, if a high-priority task is waiting on a lock held by a low-priority task, that little guy gets a temporary promotion. This priority boost makes sure it finishes its job super fast, releases the lock, and gets out of the way. The second transformation is all about taming interrupts. PREEMPT RT splits them into two parts. A tiny, super fast handler runs right away, but all it does is say, "Hey, got it," to the hardware and then wakes up a regular kernel thread. This new thread, which does all the heavy lifting, is just a normal citizen in the kernel. It can be scheduled, it can be prioritized, and it can be preempted just like anything else. The chaos is finally brought under control.
You see, by fixing these two fundamental problems, PREEMPT RT does way more than just apply a patch. It completely rewrites the rulebook for how the entire kernel operates.
Because think about it. Locking and interrupt handling are so deep, so fundamental to everything the kernel does, that changing them creates this massive ripple effect. All of a sudden, huge parts of the kernel that used to be untouchable are now fully manageable by the scheduler. Just take a look at this comparison. It really shows you the difference. On a standard kernel, right, timers run in this super high priority, untouchable interrupt context. But on RT, they run in a regular thread that the scheduler can manage. On a standard kernel, you have to use a special kind of memory allocation from an interrupt that can't sleep. On RT, since almost everything is a schedulable thread, the memory allocator can sleep, which makes it way more flexible. These aren't just minor tweaks. This is a deep architectural rewrite that makes the whole kernel more orderly and predictable. So, what's the big takeaway from all of this? The result is a kernel that is almost completely preemptible. What does that mean? It means high-priority tasks no longer get stuck waiting around for some low-priority task to finish up. The scheduler is finally, truly in charge, able to enforce those deadlines with microsecond precision. And why does all this technical wizardry matter? Well, this transformation is what allows Linux, the same OS that powers so much of the internet, to also run the critical infrastructure of our world. We're talking industrial robots on a factory floor, 5G telecom networks, medical devices, even high-frequency stock trading systems where every single microsecond is worth a fortune. PREEMPT RT basically tamed the wild, unpredictable beast that was the Linux kernel and turned it into a high-precision instrument. So now that this incredible power is part of mainstream Linux, you just have to wonder, what's the next frontier it's going to conquer?